Okay, shall we start? So, shall we start, guys? Okay. So, your Brayton cycle, or it is also called as a Joule cycle, would consist of 4 different processes. And how they look on the PV diagram, we will just try to draw one by one. So, first process is known as adiabatic compression. So, from state 1 to state 2, there is adiabatic compression. Okay. Adiabatic compression, and then the adiabatic in the sense the entropy remains same, isentropic process, so it is a straight line in case of a TS diagram. Okay, so this is 1 to 2 now. Next, after that, you have a heat addition which goes in an isobaric way. Okay, so this is an isobaric process from 2 to 3. Isobaric is represented in case of a TS diagram as some curved line like this. So it's a curved line where it reaches the state 3. So 2 to 3 is your what? Isobaric heat addition process. By the way, let us come back to this particular process from state 1 to state 2, which is adiabatic compression. Can anyone say what would be the heat flow for this? What would be the heat flow in case of an adiabatic process?
Zero.
Zero, isn't it? So just write 0 there. In case of heat addition, so heat addition from 2 to 3 happens, which is occurring in an isobaric way. So you can calculate this as mCp into T3 minus of T2. So this is nothing but your heat input. Okay. Next, again, 3 to 4 is your adiabatic expansion. So 3 to 4 happens your adiabatic expansion like this. So I can just write it as adiabatic expansion. So this particular adiabatic expansion, again, because it is adiabatic, it is 0. Since it's adiabatic, it is isentropic, so it is a straight line in case of a TS diagram there. 3 to 4. Now, from 4 to 1, again it is isobaric heat rejection. Isobaric heat rejection. So it's again a straight line like this. Just a minute. It looks something like this. And 4. Okay, so this is PV diagram, TS diagram, and as well as the various processes that happen in the Brayton cycle. Okay, so this is 4 to 1. Again, it is calculated as mCp into, now it is T1 minus of T4. So this is heat output, I can say it as. So it's heat output. Okay. Clear? So how many processes are there in the Brayton cycle? How many processes are there in a Brayton cycle?
4.
4. So 1 to 2 is what? Adiabatic compression. 2 to 3 is isobaric heat addition. 3 to 4 is adiabatic expansion. And 4 to 1 is isobaric heat rejection. So there are totally 4 processes. Now, out of all these processes, how many processes the heat would interact? That means in how many processes I could add heat or I could reject heat out of all 4? Yes? In how many processes could I add or reject heat
2
from the
processes.
system? 2 processes, isn't it? The one is where you are adding up the heat, which is Q 2 to 3. This is where you are adding heat. Now, one process where you are rejecting heat is Q 4 to 1, isn't it? So these are the 2 processes where you can add or reject heat from the system. Now, name the 2 processes where work interaction takes place. Work interaction takes place. Major work interaction. One is compressor work, correct? So this is the major work here. So you're working on the system, that is compressor work, and other work you're getting out of system is your turbine work. Got it? So 2 major work interactions are what? One is compressor work and other is the turbine work. Okay. Now, what are the 2 major heat interactions? One is heat addition, Q2 to 3, and other is heat rejection, Q4 to 1. Clear? Any doubts in this?
No, sir.
Okay. Let us move further now. Okay. The thermal efficiency, just write this, whatever I write. The thermal efficiency of Brayton cycle is given as, so efficiency of any Brayton cycle is given as, it's common for every cycle, guys. It might be your Brayton cycle, it might be Otto cycle, it might be diesel, Stirling, whatever it is a common thing. So it is net work done, okay, divided by heat input. So I can say it as net work done. I can just represent that as cyclic W divided by heat input, in the sense where are you giving the heat into the system? Q2 to 3 or Q4 to 1? Where you are giving the heat to the system?
2 to 3, sir.
2 to 3. Very good. So I will just take it as Q 2 to 3. This is where you are giving the heat to the system. Now, from first law of thermodynamics, from first law of thermodynamics, what can I say? Can I say the cyclic integral of W is equals to cyclic integral of K? Can I say that?
Yes, sir.
Right? So I would replace
can
what
be.
now? So cyclic integral of W, I would be replacing it as cyclic integral of K divided by K 2 to 3. Now further. So what are the 2 different processes where the heat interaction takes place? That is Q2 to 3 and Q4 to 1, isn't it? Any other way? So Q1 to 2 is 0 and Q3 to 4 is 0, since it is adiabatic. Correct? So I would take only Q2 to 3 and Q4 to 1. So Q2 to 3 plus Q4 to 1 divided by the denominator, which is as it is, Q2 to 3. Now, Just substitute the values of Q2 to 3 and Q4 to 1. Q2 to 3 is what? MCP into T3 minus of T2 plus M4 to 1 is MCP into T1 minus of T4. This whole divided by, it is again MCP into T3 minus of T2 for Q2 to 3. Okay. Now, finally, efficiency of Brayton cycle, what would we get? Anything would cancel here? Anything that cancels? Audio not audible. Okay. So, are everyone facing the same problem?
No, sir, it's perfect.
No, sir.
Okay, fine. Okay. Rakesh, just check your internet connection. Sir, net data pack on ಮಾಡಿ ಆಫ್ ಮಾಡು ಅಥವಾ ಏರೋಪ್ಲೇನ್ ಆನ್ ಮಾಡಿ ಆಫ್ ಮಾಡು ಏರೋಪ್ಲೇನ್ ಮೋಡ್ ಸೆಟ್ ಆಗುತ್ತೆ. Efficiency of Brayton cycle. So anything which cancels here, guys, this is very important derivation, by the way.
MCP.
Anything which MCP, very good. So I can take away whole sort of MCP. When I take it common, all this MCP will goes away. Now
T3 minus T2.
T3 minus of T2 divided by T3 minus of T2 is what? I can take it as 1, right?
1 plus
1 plus T1 minus T4.
Exactly. Am I right now? Am I right?
Yes, sir.
Okay. Now what I will doing is, just listen here. I would be replacing this particular thing. Okay, I will be just interchanging. See, what I will be doing is, I will keep all of the things in the same way. Now this T3 minus of T2, it would be in the same way, no issue. But T1 minus of T4, I would be doing it as T4 minus of T1. Okay, if I want to do such, what should I do?
Minus.
T1
Minus 1
Very
minus.
good. Very good. Excellent. So I would just replace it by minus. So efficiency of Brayton cycle is given as this particular thing, which is not the final expression though. Take it as equation number 1. And guys, I would expect you to parallelly take the notes, parallelly solve the derivation in your notes. Okay. Because this is very important. Now, next one. Take process 1 to 2, which is adiabatic. Process 1 to 2, which is adiabatic. In this particular expression, in this particular process, can you give me what is PVT conversion equation? For adiabatic process from process 1 to 2, PVT conversion equation, anyone? Okay. Anyone who knows that? So remember, I would just revise this. Isobaric, isochoric, isothermal. Okay, for all these three processes, the PVT conversion equation from process 1 to 2 is P1 V1 by T1 is equals to P2 V2 by T2. So this is the PVT conversion equation for all these three processes. Now, when you come for an adiabatic process, it is P1 by P2, that is equal to V2 by V1 whole to the power of gamma, that is equal to again T1 by T2 whole to the power of gamma
minus 1.
by gamma minus 1. Correct. So this is for adiabatic. Now, what is for polytropic? Same expression, replace it by N. So P1 by P2 is equals to V2 by V1 whole to the power of N, that is equal to T1 by T2 whole to the power of n divided by n minus 1. Now, take the expression for adiabatic process now from process 1 to 2. So, P1 by P2 is equal to V2 by V1 whole to the power of gamma, that is equal to T1 by T2 whole to the power of gamma divided by gamma minus 1. You can take all of this aside, okay, if you want it. Now, once you take that, you will be defining certain parameters now. Defining, okay, defining number 1, pressure ratio. So this particular pressure ratio will be represented by beta, and it is given by P2 by P1, or it is given by P3 by P4. P2 by P1 or P3 by P4, because P2 is equals to P3. No, just refer the diagram here. Okay, so either it is P2 by P1 or it is P3 by P4, because your P2 would be equal to P3 and P1 would be equal to P4. Either of the things you can take 2 by 1 or you can take 3 by 4. Both means the same value. Okay. Now, this is the pressure ratio what I have defined. The second thing what I will be defining is the temperature ratio. Okay. Temperature ratio, and this is given represented as T to the suffix R. And it is given by same thing, guys. Same thing. Okay. It is given as T2 by T1, or it is given as T3 by T4. Okay. From this, can I just write, replacing now T3 by T2 T3 by T2, that is equal to T4 by T1. Can I write it as such? Any problem in writing this? Any problem? Just I have replaced the numerators to denominators. Okay.
No, sir.
Okay. So now I would be calling this particular equation as equation number A. So substituting parallelly, you have to take down. Substituting in equation A. So what are you going to substitute there? So you have there P1 by P2, that is equals to T1 by T2 whole to the power of gamma divided by gamma minus 1, isn't it? Now, P1 by P2, P2 by P1 is beta. So what is P1 by P2 though? 1 by beta? Correct? Next. What do you mean by T1 by T2? T2 by T1 is TR. What is T1 by T2? 1 divided by TR. This whole to the power of gamma divided by gamma minus 1. Okay. Now, interchanging both LHS as well as RHS, numerators to denominators, can I write beta is equal to TR into gamma divided by gamma minus 1? Can I write it as such? Any problem? Understood this particular concept? Any doubts here? Any doubts?
No, sir.
No, sir.
Okay. Now, if you
Sir.
take the expression,
ಅದು ಟಿ ಆರ್ ಪವರ್ ಗಾಮಾ ಮೈನಸ್ 1 ಬೈ ಗಾಮಾ ಆಗಲ್ಲ ಸರ್.
ಏನಕ್ಕಾಗುತ್ತೆ ಗಾಮಾ ಮೈನಸ್ 1 ಬೈ ಗಾಮಾ? ಏನಪ್ಪ?
ಅದು TR ಮೇಲೆ ಬಂದಾಗ ಅದು ಪವರ್ ಚೇಂಜ್ ಆಗಲ್ಲ ಸರ್.
ಅಲ್ಲ, ನಾನು ಬರೀ RHS ಮಾತ್ರ ಮೇಲೆ ತರ್ತಾ ಇದ್ದೀನಾ. ಇವನ್ ಐ ಆಮ್ ಬ್ರಿಂಗಿಂಗ್ ದ LHS ಆಲ್ಸೋ, ನೋ?
ಓಕೆ ಸರ್.
ಸೊ ಇಟ್ ವಿಲ್ ಕಾಂಪನ್ಸೇಟ್. ಅರ್ಥ ಆಯ್ತಾ?
ಎಸ್ ಸರ್.
Now, take the equation number 1. Take equation 1. What was the equation number 1, guys? Anyone? Efficiency of Brayton.
1 minus T4 minus T1 divided by T3 minus T2.
Thank you. T3 minus of T1 na T2?
T2. T3 minus T2.
T2. Okay. So now what you do, see the modifications what I do now. Okay. Now, 1 minus, I would keep the numerator as it is, T4 minus T1 divided by. I would take T2 common. If I would take T2 common, if it is not there T2, then it would be T2 here, minus of 1. Correct? Yes or no?
Yes, sir.
Now, I would take this particular expression as C, and I would write from C, what can I write? 1 minus T4 minus T1 divided by T2. ಯಾರದು? ನಾಗೇಂದ್ರ. Done. ಈಗ T2 into T3 divided by T2 na, can I write it as T4 divided by T1?
Yes, sir.
From equation number C. So it is ಏನಾಯ್ತದು? T4 divided by T1 minus of 1 close one. Next, take LCM here. 1 minus T4 minus of T1 divided by T2. Now you take LCM. T1 is LCM. It is T4 minus of T1. Correct? Anything that cancels here now. ಏನಾದ್ರೂ cancel ಆಗುತ್ತಾ? Anything would cancel here? Anything would cancel? Nothing would cancel? Okay.
T4 minus T1.
Correct ತಾನೆ? So T4 minus T1, T4 minus T1 cancel ಆಗುತ್ತೆ. So it would be what? It would be something like this. 1 minus 1 divided by T2 by T1 ಆಗುತ್ತೆ. Correct? So what do you mean by T2 by T1? T2 by T1 is nothing but TR, no? ಹೌದಾ ಇಲ್ಲ?
Yes, sir.
Now, from equation B, ಇಲ್ಲಿ ನೋಡಿ, beta is equals to TR into TR to the power of gamma minus gamma divided by gamma minus 1. ನನಗೆ ಈಗ TR ಬೇಕು. ಸೊ ಈ gamma divided by gamma minus 1 ಅನ್ನು ಆಚೆ ಕಳಿಸಿದಾಗ ಏನಾಗುತ್ತೆ? When you send an A by B which is in power,
Gamma minus 1 by gamma.
Very good. So when you send A minus B to the either side of your LHS of a power, then it would be reciprocal of it. It is gamma minus 1 by gamma. So same thing ನಾನು ಇಲ್ಲಿ ಬರೀತೇನೆ. So that is equal to 1 minus 1 divided by beta to the power of gamma minus 1 by gamma. Efficiency of Brayton cycle. And even this is also efficiency of Brayton cycle. So efficiency of Brayton cycle. Any one of these three expressions you can use in your problems. Okay. So this particular expression is in terms of the temperature ratio. Yes or no? So this is in terms of the temperature ratio. And this particular expression is in terms of a pressure ratio. Okay. So in the problem, he might ask any of the thing. See, in terms of pressure ratio and temperature ratio, for both we have find it out. So if you just ask us to derive an expression for the thermal efficiency of the Brayton cycle, even for that also you need to do all this up till here. At the last, you can write a conclusion statement for this is...
Sir, whether into 100 will come?
Into 100 will definitely come if you want it in percentage. Okay. Is the required expression for efficiency of Brayton cycle in terms of pressure ratio and temperature ratio. Just write the conclusion statement and end your derivation. Okay. And this is very, very important derivation. Okay. There are totally 3 derivations in this particular module. All of 3 are very, very, very important. Okay.
So show that from first derivation.
Huh? Enappa?
So derivation show first from first.
From first to?
Derivation sir ತೋರಿಸಿ first in.
ತೋರಿಸ್ಬೇಕಾ? Okay. Anyhow, we will be getting notes. Don't worry. Have you checked the notes of module number 1 which I have sent in the Google Classroom?
Yes sir.
Anyhow, we'll be getting the notes. Okay. So please take the screenshot. We have to move further. Please take up the screenshot. So that's why I told you, whenever I'll be solving the problems, isn't it? So parallelly, you have to complete your notes writing. I'll be writing very slow. Yes or no? Because it's difficult to write on this iPad and all, so I'll be writing very slow. So you can easily write it. Okay? Parallelly. Shall we move? Nagendra, aitena? Munde hogoಣ?
ಆಯ್ತು ಸರ್ ಆಯ್ತು.
Okay. Now, let us just come back and analyze our Brayton cycle once again. Okay. So this was our Brayton cycle, isn't it? Something like this. Okay. So this was our state 1. This was our state 2. This was our state 3. And this was our state 4. Now 1 to 2 was adiabatic compression. 2 to 3 is isobaric heat addition. 3 to 4 is again adiabatic expansion. And 4 to 1 is isobaric heat rejection. So heat gets in isobarically from 2 to 3. Heat gets out isobarically from 4 to 1. Work gets in adiabatically from 1 to 2. Work gets out adiabatically from 3 to 4. Getting it? So this is all the process what you have learned. Now we shall discuss how to calculate your work done in Brayton cycle. Calculation of work done in a Brayton cycle. Okay. Now, there are 2 major work. So one is the compressor, where you compress the things, and one there is a turbine where you expand the things. Okay. So the number 1 is the compressor work. Okay. Which is represented as WC, or it is given as W1 to 2. That is given by, it is simply MCP T1 minus of T2. Okay. Second one is the turbine work, Second one is the turbine work. So that is given as MT, the WT. W3 to 4 is your turbine work. So it is simply given as MCP into T3 minus of T4. That's it. Okay. Now, if you observe this, okay, this is a very important line what I'm going to write here. Very, very important. Very, very important. Okay, what is that important line? If you observe, for work calculation, okay, for work, it is always initial minus of final. When it comes for the heat, it's final minus initial. Yes or no? When it comes to the work, it is what? It is initial minus of final. For example, you take this particular thing. Okay. State 1 to state 2. So this is your initial. Correct? And this is your final. Okay. So MCP, initial minus of final. 1 minus 2. Can I get? Suppose if you want to calculate heat flow from Q2 to 3. Okay. If you want to calculate the heat flow from 2 to 3, how would you do? Anyone? MCP. For heat, it is final minus initial. So this is your final value and 2 is your initial value. So can anyone give me the expression to calculate heat flow from 2 to 3?
minus 2. T3 minus T2.
Exactly. It is T3 minus of T2. This is how it works. So for heat, it is initial minus final. And for work, for heat, it is final minus initial. And for work, it is initial minus final. So kindly take all this stuff in a box. It's very, very important. Okay. Now, understood up till here? Any doubts? Any doubts? Okay. Now, we shall try to analyze the concept of actual Brayton cycle. So what is this actual Brayton cycle? First of all, what was our ideal Brayton cycle? Something like this, right? This was our PV diagram. It has to be a curve, guys. I will just try to draw a curve. Something like this. Okay. So this was our state 1, state 2, state 3, and state 4. Similarly, when I try to draw a TS diagram, it is something like this. Okay, TS. Correct? So 1 to 2 was adiabatic compression, which is this. 2 to 3 is this. 3 to 4 is this. And 4 to 1 is this. So this particular cycle, what we have analyzed up till now, was an ideal thing. Ideal thing in the sense which was supposed to be happened according to the papers. Which was supposed to be happened according to the experimentation. Do you think the actual Brayton cycle would be as similar to the ideal Brayton cycle? There would be a little, at least we can expect a little deviation, isn't it? Yes or no? Are you able to understand it? Suppose, look here. So according to your calculation, your expectation, if your compressor is 100% efficient, then it would make the state 1 to reach at state 2. If your compressor is how much? 100% efficient. Suppose if it is not, do you think it would trace the same line, or it would something deviate like this? You cannot expect your compressor to be 100% efficient. Yes or no?
Yes, sir.
So since your compressor is not 100% efficient, definitely it would not trace this particular line there. It would deviate like this, correct? Yes or no? So that's why, so 1 to 2. Okay. So 1 to 2 is your ideal thing. Okay, I can just write process 1 to 2 is ideal compression. Ideal compression ends in the sense it was supposed to happen. But what happens because of ineffective compressor? It will just deviate its path something like this and reach the point 2 dash. Similarly, I can show it in the TS diagram also. It would just deviate a path like this to hit at state 2 dash. Now I could say 1 to 2 dash is the actual compression. Okay, got it? So this is the story of the compressor. Do you think even the turbine would be 100% efficient? Do you think the turbine to be 100% efficient? If it was 100% efficient, it would have traced this particular line, which is 3 to 4, isn't it? But none of the machines in this universe is 100% efficient. That's why your turbine would trace this particular curve, which meets at 4 dash. Which meets at 4 dash. So even in the TS diagram, I can show the 4 dash here. So this is your 4 dash. This is your 4 dash. Got it? So in case of the expansion, I would write the process 3 to 4 is what? It is ideal expansion. Okay. Whereas ideal in the sense, I can even write it as isentropic. It is isentropic expansion. Even this is isentropic compression. Okay. Whereas the process 3 to 4 dash, 3 to 4 dash is what? Your actual thing which is happening, which is an actual expansion. Actual expansion. And this all happens. It happens. Why it happens? Anyone? Why there is a difference between an actual thing and an ideal thing? Why it happens? Anyone? Why this particular thing happens? Anyone?
Loss of energy.
I can just say it happens because of ineffective compressor and turbine. Yes or no? Because of the inefficiency of the compressor and turbine, this particular thing happens, isn't it? Now, it's the time to define my compressor efficiency and turbine efficiency. Okay. Compressor efficiency, and even you have to define your turbine efficiency. So how would you define it? It's very, very simple. It is just given by eta to the suffix c, and it is given by isentropic work divided by actual work. Okay. What is isentropic work? What is isentropic work? Isentropic work in the sense, this is ideal work. So this is 1 to 2. So I can write it as H1 minus of H2. So I would just write that. It is H1 minus of H2. Actual in the sense where the dash comes there, isn't it? So where the dash comes, what is actual? The deviated path. So deviated is 1 to 2 dash. So here I can write H1 minus of H2 dash. That is your work, which is actual. So it is H1 minus of H2 dash. In terms of temperature, I can also write it as T1 minus of T2 divided by T1 minus of T2 dash. Clear? Now we will come for the turbine efficiency. So the turbine efficiency is nothing but it's exactly reverse of compressor efficiency. It is actual work divided by isentropic work. It is actual work divided by isentropic work. Now, let us calculate actual work, which is 3 to 4. 3 to 4 is actual thing, right? Can I write it as H3 minus of H4? Actual work in the sense this one, right? So can I write it as H3 minus of H4 dash? Right? For the actual work of turbine? Yes or no?
Yes.
Yes.
So just I would write what? Actual work in the sense it is H3 minus of H4 dash divided by it is H3 minus of H4, which is the isentropic one. Remember, whenever there is a dash, it indicates it is a deviated path. Whenever there is a dash, it indicates it's a deviated path. Deviated path in the sense it is not ideal, it is not more ideal, it is an actual thing which is happening, which is deviated, which is actual thing which is happening. In terms of temperature, I would write it as just change it as T3 minus of T4 dash divided by T3 minus of T4. So these expressions are very, very important for the problem solving. Okay. Understood about the actual Brayton cycle, how the deviation occurs, and how to calculate your efficiencies? Any doubts in this? Any doubts? If you have any doubts, we'll discuss, or else we'll end the class. Okay. Okay. CS. So all of you just fill up your attendance sheet.
Sir,